Good afternoon. My name is Thomas Randolph, and today for global climate change mitigation, we're going to be talking about feedback loops, albedo, and melting permafrost. And each of these different topics are very relevant to mitigation because by mitigating, by slowing down climate change, we have an opportunity, hopefully, to slow some of these processes that we're going to learn about today and slow some of these processes down. So let's start with albedo and feedback loops. Albedo is the ability of the Earth to reflect energy or light back out into space. So albedo is snow and ice would be a good example of that. The ability for the sun's energy, as you see on the picture here on the right-hand side, the sun's energy comes in and that shortwave radiation, it strikes the snow. The snow reflects that shortwave radiation back out into space, or at least a portion of it. Now, on the left-hand side, we see another picture here. The sun's energy, that shortwave radiation, impacts the Earth, and then it's transformed into heat and also long-wave radiation. That long-wave radiation is then also emitted up into the atmosphere where it interacts with greenhouse gases. And those greenhouse gases then redirect a portion of that warmth, that long wave radiation, back down to Earth. So that's where albedo plays a part in it. The other system we're talking about are the feedback loops. And feedback loops can be a negative feedback loop would diminish a process. A positive feedback loop increases a process, just like interest in a bank. You have interest, the more interest you have, the more money you have in the bank, the more money you have in the bank, the more interest you earn. The only thing is, for our purposes today, we're going to be looking at feedback loops and albedo in an area of about 50 million square kilometers in the northern latitudes. And we're going to be looking at how these processes interact with each other and really how little we know about them. So let's look at a feedback loop that's really relevant to what we're talking about. At the top of the picture here, we see temperature rising. So as the temperature rises, permafrost up in the northern latitudes begins to melt. As it melts, it gives off certain greenhouse gases like methane, CH4, and also carbon dioxide, CO2. As those enter into the atmosphere, they again reflect that long wave radiation back down to the Earth, which then increases the temperature on the planet. As the temperature goes up, more permafrost melts. As more permafrost melts, more CO2 and methane get released, which increases the temperature even more, which causes more permafrost to melt, which then increases the process. So that's a quick example of a very relevant feedback loop related to permafrost and albedo. This picture gives us a very clear, tangible example of permafrost melt. So we're talking about two different systems here. We're talking about we're talking about the albedo, the ability of the planet to reflect shortwave radiation before it becomes long-wave radiation and heat, and also a process that involves creating greenhouse gases and increasing the temperature of the planet. So as the permafrost melts, it gives off that CO2 and methane. But what is permafrost? It's basically the remains of animals and plants that have been frozen for thousands and thousands of years. This material may thaw out a little bit here and there, but overall it has never really completely thawed out. But what we're seeing now are these increases in temperature, which is allowing this material to thaw out, which is then starting a process with microbes that is releasing more greenhouse gases and creating more feedback loops. So let's take a minute and think about how these things interact. When we think about the albedo of the planet's ability to reflect shortwave radiation back into space, well, as temperatures increase, we start to see less albedo, and that, of course, causes more temperature increase. We also start to see more methane and carbon dioxide being released from permafrost, again, because of temperature increase, which then reduces our albedo, which then increases temperature again. So we can see that these things can work together synergistically. They can really multiply as positive feedback loops. So what about just the numbers? So when CH4 is released into the atmosphere, it increases radiative forcing as much as 85 times more efficiently than the same amount of CO2. So pound for pound, methane is a much stronger greenhouse gas. Also, what about concentrations of carbon itself? In the permafrost, it's estimated that there are about 1,600 billion tons of carbon sequestered in the permafrost right now. There's also been some recent studies that have found something called deep carbon, which is carbon that's sequestered more than 3 meters down in the permafrost, which is also a considerable concentration of carbon that can be released. Again, reminding us why mitigation is so important as we move forward. So let's take a look and see how is this carbon being released into the atmosphere. It's not being burned up there. So what's putting it from the permafrost just because it's melted, putting it into the sky? Well, greenhouse gases are released from the permafrost as a result of microbial processing. And there are the anaerobic, so with air and without air. Uh, the anaerobic is without air, the aerobic is with air. And what we're talking about here is really how water plays a role in all of this. So water is a result of the melting ice. And what researchers have found as this permafrost starts to melt, it's creating seeps and creating things that are called moats. And this phenomenon is starting to interact with the soil, allowing microbes to start processing the carbon, and the carbon then is released as a gas, carbon dioxide, into the atmosphere through this microbial process. So how do they measure the amount of carbon dioxide and methane coming out of these permafrost areas? How are we getting to this data? So this researcher is standing by a permafrost moat type area, and we can see the water in there as well. And what they do is in this example, they take a sensor, an extremely sensitive sensor, a sensor that can detect greenhouse gases, and they insert it about 25 centimeters into the permafrost. And they begin collecting this data. And they're looking at both the anaerobic without air and the aerobic with air, so the water covered and water uncovered areas. And what they're finding is that the CH4, the methane, was more abundantly released in these moated areas that are saturated with liquid water, so these anaerobic environments. And the research indicates that permafrost could play a substantial role in radiative forcing uh, and long-term climate change as we move forward. Another way we can get at this data is not by looking forward, but looking to the past. In this picture, we see an ice core. And in the ice cores that are buried deep down in the permafrost and in the ice fields are bubbles. And these bubbles contain samples of what the atmosphere was like when this ice was formed. And what was interesting is that some of these samples showed very low levels of methane, indicating that there's a good chance that there were microbes that were actually consuming the methane and also releasing a product, again, carbon dioxide. And it may have provided these high latitude microbes with food for a long, long period of time. So we see that it's not just methane that's being released, but it's also carbon dioxide that's being released. And the carbon that's stored in the permafrost is really the fuel for this whole process that's happening in the microbial world today and also thousands of years ago. So let's take a look at some of these microbes here on the right and start to think about this fuel. So permafrost contains up to 80% carbon, and carbon is decomposed by high latitude microbes. They convert carbon into CO2. Microbes then release it into the atmosphere, and therefore this adds to radiative forcing. And radiative forcing, again, is that energy that's coming into the balance system of our planet, the balance between heat and radiation coming in and heat and radiation going out. And we get into the Stefan Boltzmann's constant to kind of dig into that a little bit more. So these microbes release this into the atmosphere, and therefore this adds to radiative forcing. Other research indicates that even small percentages of permafrost thawing will increase radiative forcing due to the release again of these greenhouse gases. So it's something we really need to be thinking about when we think about why are we so concerned about mitigation today? Why are we so concerned about having laws in the state of California and other states to bring down our greenhouse gas emissions and hopefully reduce climate change? Well, one of the reasons we're in such a hurry, why are we so concerned about this, is because these other feedback loops are also happening synchronistically with our mitigation and our greenhouse gas emissions today. So as radiation comes in and goes out of our planet's atmosphere, we should be thinking about what our researchers here in this study have shown us, that anthropogenic climate change, human-caused greenhouse gas emissions, pushing our temperatures up, is accelerating other systems that we know very little about, like melting permafrost and albedo, loss of that reflective cover of snow and ice. So as we move forward, we should be thinking about things that we still don't even completely understand. And there's a principle known as the precautionary principle, which may be something that we should be thinking about seriously applying as we think about the seriousness of mitigation. So in conclusion, we really need to be thinking more about our mitigation practices and really bringing into the conversation things like more rapid temperature increases happening in higher latitudes where there are less people, but there is very vulnerable permafrost, which is perpetuating a positive feedback loop that is releasing more and more greenhouse gases as we speak. Along with that, another positive feedback loop, the loss of albedo, is reducing the planet's ability to reflect shortwave radiation and also increasing temperature, which then, of course, reinforces itself as a positive feedback loop. So when we think about mitigation and why are we in such a hurry to reduce our greenhouse gas emissions, we also have to consider these other feedback loops that are happening on our planet today.